Let's continue this lecture on section 14.3. This is the home stretch. I'm just going to go from here to the end, even if it takes 20 minutes to get there. So in the last section, we talked about how we can decompose every permutation into a series of transpositions. Okay. In this lecture, we're going to take note of the fact that when you do decompose a permutation into a series of transpositions, you either get an even number of transpositions or you get an odd number of transpositions. So if you have a sequence of transpositions that gives you a permutation and it's an even number of transpositions, then you'll never find for that permutation an odd number of transpositions it'll get for you, and vice versa. Okay, so Theorem 2 is all about that. This is a rather involved proof. In order to really get this proof done, what we need to do first is we need to talk about some terminology. One, we're going to call permutations odd permutation if it takes an odd number of transpositions, right? And we're going to call it even if it takes an even number, okay? Even number of transpositions. And then we're going to say the sign of these is -1 and the sign of this is +1, and you can calculate the sign by just taking -1 times the number of transpositions it took to decode the permutation, okay? Where do we go from here? Well, first let's talk about orbits. Okay, what's an orbit, right? So if we took a transposition, right? Let's say in this case we have not a transposition, a permutation. Sigma is equal to very naughty handwriting. 1, 2, 3, 4, 5, and 3, 5, 4, 1, 2. Okay. Take note of what happens when we take sigma of 1, that gives us 3. Sigma of 3 gives us 4, and sigma of 4 gives us 1. Okay? Or in other words, if we start with 1, and we take sigma and apply that to 1, and then take sigma twice and apply that to 1, and take sigma 3 times and apply that to 1, after applying it once, we get 3, twice we get 4, and 3 times we get back to 1. And as you might expect, sigma 4 is going to give you back 3, sigma 5 is going to give you back 4, and sigma 6 times applied to 1 is going to give you back to 1. So there's this cycle, there's this looping that happens when you apply the permutation again and again. Okay, let's draw a picture of what this might look like. So we have a circle. We start at 1, we go to 3, we go to 4, and we go back to 1. Okay, so this is what happens every time we apply sigma. Okay, so this would be sigma squared and sigma to the 5th. No, sigma to the 4th. Sigma, not squared. Sigma to the 1st and sigma to the 4th power. This would be sigma squared and sigma to the 5th power. And this would be sigma to the 0th power, which is the identity, or sigma to the 3rd, or sigma to the 6th. Okay? So what we're saying here is that for certain numbers, if you apply the permutations multiple times, you're going to find that it's going to form a cycle. Why do we know it has to form a cycle? Well, think about it. If we have a sequence of permutations, so we start with I, then we go to sigma of I, then we go to sigma squared of I, and all the way up to some number. Okay, we do this infinitely. Well, there are only so many numbers you can have because sigma is only defined it's only working on Jn. So you can have at maximum n permutations before you get back to the original number, right? That makes a lot of sense, doesn't it? Now, typically with a permutation, you don't get n, you get some smaller number of n for each number. Okay, so what we'll do is we'll define a couple numbers here. Let's say that we had two numbers. We had s and r. Okay, and we found that if we applied the permutation r times to the number I, we get sigma applied s times to the number I. So we found a cycle. Okay, and so we can say I is what you get after applying the permutation s minus r times to I. What we've done here is we've just multiplied the right side of each of these by the inverse of r. Okay, so we get sigma of s minus r will give you a cycle. Is this the smallest cycle? Not necessarily, but we're going to introduce this new number k. K will be the smallest integer such that I is equal to sigma ki. Okay, so this is the number that'll give you the smallest cycle. In this case, k is equal to 3. Okay, and we can use different numbers for s and r, and we can see how we can recover I again. Now, we're going to prove right now that there is the smallest k. There is no number smaller than k. And the way we're going to prove this is by contradiction. So we're going to prove that k is the smallest number. So let's say we have two numbers m and n. M is less than n. N could be equal to k. M could be equal to 1. And we find somehow that sigma m of I is equal to sigma to the n of I. So we found some cycle between m and n where these numbers are smaller than k. So the difference between m and n is obviously smaller than k as well. Okay, and so we would get sigma of n minus m of I should give you back I. Okay, and if n minus m is smaller than k, then k wasn't the smallest integer, right? So therefore, these numbers have to be 1 and k, right? They can't be any other numbers, right? All right, now we're going to go to the general case. Let's draw a circle to represent all the orbits. We call these orbits, okay? So we start with I, and then we go to sigma of I, then we go to sigma squared of I, dot, 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 all the way up to sigma of k to the minus 1 of I, which will bring us back to sigma of k, which is the same as I. Sigma of k is going to give you I back. Keep in mind that sigma of k is not the identity. Only for this one value it gets you back the thing that you wanted, okay? And so we're going to describe this orbit. We're going to use the symbol gamma, okay? And this is going to be the number I, sigma of I, sigma squared of I, all the way up to sigma of k to the minus 1 of I. Okay, so all of these numbers belong to this orbit, okay? And we'll call this the cycle of the orbit, okay? Now, k is going to be called the period. That tells you how many elements are in the orbit. In this case, there are k items, right? There's 0, 1, 2, 3, 4, 5, all the way up to k minus 1, okay? We can also call this the length, okay? The length of the cycle. As an example, let's look at some different permutations. Let's find the orbits and let's describe them. So we have sigma is equal to 1, 2, 3, 4, 5, 3, 5, 4, 2, 1. 1, 2, 3, 4, 5, 3, 5, 4, 1, 2. Okay, so let's look at one orbit. So we have one orbit that starts at 1, it goes to 3, 3 goes to 4, and 4 goes back to 1. So that's one orbit. There's another orbit, 2 goes to 5, and then 5 goes back to 2. So we have two orbits. This one has k equals 3. This one has k is equal to 2, and they're different. Okay. Now we could describe this permutation uniquely. In fact, you'll note that the cycle 1, 3, 4 is the same as the cycle 3, 4, 1 is the same as the cycle 4, 1, 3, and 2, 5 is same as the cycle 5, 2. Okay, all of those cycles are the same. Okay. What about the identity? What is the cycles there? Well, the identity has n cycles, one for each element of Jn, okay, and they only have one element, being each number of Jn has its own cycle because the numbers just go back to themselves. They don't go to any other number. What about a transposition, right? Let's say we have a transposition that switches A and B, okay? In this case, you will have you'll have multiple orbits. You're going to have n minus 2 cycles that behave like the identity. It's just I for those. And then you're going to have another cycle, one cycle, that has A and B in it, right? Okay. Notice what happened when we introduced a transposition here. The number of cycles from the identity went from n to n minus 2 plus an additional cycle. So this guy has a total of n minus 1 cycles. In fact, this is what we're going to use to prove that there is going to be an odd or an even number of transpositions for each permutation. Okay. In order to get there, let's first talk about the orbit decomposition. So we can describe a permutation as kind of the union of those cycles, 1, 3, 4, and what is the other one? 2 and 5, for instance, would describe this one here, okay? This orbit decomposition is a description of sigma. If you have theorem 3, let's do theorem 3. Theorem 3 is a little bit fun. Okay, theorem 3 states that if A and B are elements of Jn, and sigma is a permutation of Jn, then the orbits to which A and B either coincide or have no element in common. So the orbits containing A and B, there is either one of them that's unique or there's two of them and they're different, okay? And so the proof here is a little bit involved. It's not terribly complicated. I think already just thinking of this and thinking of what we learned, you have some idea on how you can prove this, right? Okay. So suppose that the orbits have the elements in common, okay? This means that in the orbit that has both of these elements, you have some orbit with like an A in there and a B in there, okay? Or it could be the other way around, either way. That means that you'll take sigma applied to itself R times on A, and you're going to get sigma applied to itself S times and get B, okay? These two numbers will be the same, okay? And so we can say A is equal to sigma of S minus R applied to B, okay? Thus we see that A occurs as some sigma m of B, so this is an integer, okay? And that means that we have sigma of A is equal to sigma of, let's say S minus R is equal to m plus 1 applied to B, okay? And sigma squared of A is equal to sigma of m plus 2 of B. And you can see how these two are just chasing each other as you cycle through this orbit, okay? And eventually you'll get back around so that you'll see that these are actually part of the same orbit. You can actually walk through this orbit and find that you'll get back to the elements that you've seen before, okay? If we can't find any numbers such that this ever happens, then that means that these guys are in completely different orbits, and so you cannot write them, you cannot find an orbit that contains both of them for the same reasoning that you could find an orbit if they were powers of each other, okay? To continue our proof of Theorem 2, let's consider what happens when we apply a transposition to a permutation, right? What happens to the number of orbits, okay? So in case 1, when we apply that transposition, okay? So the transposition is basically moving A and B. So that's what tau is doing, okay? In case 1, the two numbers A and B belong to the same orbit. So A and B are in the same orbit. What are you doing when you apply this transposition there, okay? So let's write down, we say that the sigma can be decomposed to a bunch of gamma. So gamma 1, gamma 2, gamma 3, all the way up to some number gamma m, right? Okay. Each of these are orbits, okay? So the question is, what happens? So gamma 1, let's suppose gamma 1 is that orbit that contains A and B, right? So gamma 1 is described by integers. It has numbers that go from I to the 1 all the way to ik. So there's k integers in this orbit, okay? And let's suppose that our tau, we're switching elements A and B, where A is in this series, and this is the rth element, and B is in this series, and it is the s element. Obviously, R has to be less than k. And we're just going to pretend that B is less than, A comes before B. So we're going to say also that R is less than S is less than K. Okay, so it's going to be like some numbers, and then we're going to have A, and then some other numbers have B, and then we're going to go back to the last number, and then it's going to cycle back to the beginning. Okay? Let's express what happens when we apply tau to gamma, to this gamma 1. Okay? So think of it this way. So gamma 1, we're going to break this up. We're going to start with the first I, and then it's going to go up to the rth I, and then it's going to go up to the si, and then it's going to go up to I to the k. Okay, so if we apply tau to that, what's going to happen to the cycle? So we're going to go up to this element r, and then when we apply, nothing's going to change, right? So all these numbers are going to be the same because tau doesn't touch any of the numbers except for a and b. And when it hits a, that first element there, it's going to substitute in s. Okay, so this one is going to go to I to the s. Okay, and what is that going to do? It's going to cut out and skip all of that stuff and continue to k and then go back to there. So it's going to have one cycle that goes from I to the 1 all the way to IR, and then IR goes to IS, and then it's going to go to IK, and it's going to go back to 1. Okay, basically cut out those guts. And there's going to be another cycle inside here. Oh, no. I'm sorry, I made a mistake. So it's going to go to R minus 1, and once you hit IR, it's going to go up to S, right? And then the other cycle is going to start at IR, go up to I to the S minus 1, and then cycle back to IR. So we have created from this one cycle, we've created two cycles. We're going to call this one gamma 1 prime. We call this one gamma 1 double prime. Okay, and so now we can express tau sigma as the combination of tau with all the gammas, and that is going to be gamma 1 prime, gamma 1 double prime, and all the other gammas, because they don't have A or B in them, they're just going to be as normal. Okay, so in this case what we've done is we've added one more cycle. Okay, in case 2, A and B are in different orbits. Okay, so let's consider for case 2 that we have the gamma 1 orbit has numbers I1 all the way to IR, cycles back. Gamma 2 has numbers I1 all the way to IS and cycles back. Or let's call these J actually, so that we don't get them confused with each other. Okay. If A is in here and B is in here, what's going to happen is we're going to go from gamma 1 up to that element A, okay, and then that's going to jump over to this sequence, continue here, which is going to go back and then hit this B element, which is going to continue from here and then go back here and jump back there. So basically, we're going to have a new sequence. Let's call it gamma, let's call this gamma 1, 2 prime. And so it's going to go from I1 all the way up to, let's say, A is equal to let's see, we're running out of letters, IT, and B is equal to IU. So it's going to go up to IT minus 1, and then it's going to start with IU, okay, because A goes to B. Then that's going to go to IS, which is, or JS. This is J, actually, J, which is then going to go to J1, and then go all the way up to J of U minus 1 right before B, and then once you hit B, then it's going to continue with IT, which is going to go to IR, and that's going to cycle back to the beginning. So we've basically taken these two sequences that composed sigma and we've joined them together. So now we have minus 1 cycle. Okay, so the net effect is that each transposition can either increase or decrease by 1 cycle. Okay, so if you have sigma with, let's say, 6 gammas, okay, in order to get to the identity, you need n gammas. Okay, so how many transpositions does that require? That's going to require number of transpositions is going to be number of elements in the sequence is the maximum number minus the number of orbits. Anyway, guys, this is a really fun problem to look at and think about. And the long and the short of it is we can introduce Theorem 4, which allows us to predict whether a permutation is even or odd just looking at the largest orbit, or number of orbits, right? So suppose sigma has k orbits. Then if, and j of n, right? So if n minus k is even, then the permutation is even. If n minus k is odd, then you have an odd sigma, okay? And the proof of this is rather simple. just thinking about how the number of transpositions influences the number of cycles, and seeing how many it would take to get back to the identity, which has n cycles inside of it. Anyway, the exercises are pretty fun. I wouldn't take this too seriously or think too hard about it. There is a problem number 11 that was very interesting. Okay, and what this problem number 11 says that it allows you to prove that there is a number of possible permutations for each jn, and that's going to be n factorial. Okay. And so if there's one takeaway you take from this chapter, it's like if you have n elements, the number of ways you can permute those elements is just n factorial, okay? And so there's if you read, I think it's chapter 16, talks about proof by induction. Yeah, chapter 16. If you read proof by induction, you can be able to definitively and concretely prove for yourself that the number of permutations is n factorial, okay? And hope you enjoyed these exercises. Guys, I hope you got something from this lecture. I hope you enjoyed a little bit more about mathematics and where it can go, what you can do with it. Anyway, take care and bye-bye. This video was part of my series on Basic Mathematics by Sergey Lang. Be sure to subscribe and ring the bell, like and share this video. You can find me on Discord and support me on Patreon. Thanks a million.